Hello friends, in our previous lecture we saw that even though we begin with the description of what a derivative is, it is possible for us to formulate the expression two different ways. Now the conventional description of any given derivative for a function is how the function changes as the variables that dictate it varies. So if you consider a univariate function such as this f of x, the derivative of the function d of f of x with respect to x. So this is a univariate function. It is exclusively dependent on how the x value changes. So in that case, the derivative of this function is dependent on the value x assumes. So as the value of the x changes, the correspondingly the function changes, and how the function varies is what we refer to as the derivative. Now this description allows us to have an expression of this sort, which can be expressed as this. So in the numerator, what we essentially have is how the function, what is the value of the function when the variable changes from x to x plus delta x. So in the numerator we have two distinct terms. The first term is the function at a position that is greater than that of the original position. So the original position is x, and we consider an additional position x plus delta x. This is greater than the original position, and we find the function at this new position of x plus delta x and treat it as the first term in the numerator. We treat the function at the original position as the second term in the numerator, and in the denominator we consider the distance separating these two terms. So this is a definition and a description that we arrive from, or an expression that we arrive from the way we describe a derivative, and this is an approximation. This is approximately equal to, the derivative is approximately equal to this difference and the ratio with respect to delta x. Now here what we are considering is, so a characterizing feature of this way of expressing a derivative is we are considering a term that is greater than, in addition to the original x value, we are considering a position that is greater than the original x value. We are considering a point, we are considering a x value that is on the right hand side of the x. So if you consider on the x axis how the x value varies, if the x, the point that we are interested in here, we are considering a point that is greater than the actual point, that is x plus delta x. So in this case we are considering a new point that is beyond or towards the right of your original point, and therefore we refer to this as a forward difference expression. So what essentially we are doing is we have a description for derivative, and this description we are translating it to a numerical or a mathematical expression, and while translating it, in this expression comprises of two terms in the numerator and one of the terms in the numerator that involves a new point that we have considered. This point is greater than the original point, and therefore it is towards the right of the original point. It is forward to the original point. So we are considering a point that is beyond the original point, forward to the original point. So therefore this expression is referred to as the forward difference expression. So as your point moves forward, as we consider a point that is forward to the original point, how the function varies is what we are considering in the numerator, and we are taking the ratio of it with respect to the difference in the 2 points that we are considering, ultimately leading us to the derivative of the function. Now we saw it is also possible for us to consider a point that is rather less than the original point. So value of this, a point, that new point that we are considering is less than the original point, so it is x minus delta x. So it is also possible for us to consider a point that is behind the original point. So if you assume this point to be forward, so this point is rather behind the original point. So it is, we are moving backward. So in the first case we are moving forward to find the new point. In order to estimate the derivative, we moved forward. Now in this case, in order to estimate the derivative, we are moving backward. So the derivative of this function when we move backward to find a new point is of this form, that is f of x minus delta x divided by delta x. So what we have is, we move forward to arrive at this expression, we move backward to arrive at this expression. So what these two expressions are is, these are the approximation of the derivative. So what you find here is not an equal sign but an approximation sign. So what we are trying to do is, instead of finding the exact derivative of a function, we are trying to approximate it by considering a point next to the original point. This point next to the original point can be arrived at by either moving forward or moving backward. So therefore, even though we start from a single point of the definition of the derivative, by the way we move, we arrive at two different expressions. And since both these are approximation of the actual derivative, these approaches are referred to as the backward difference approximations or forward difference approximations. So these are two different approximations, and these approximations, the fundamental principle that differentiate these approximations is, we need a point that is different from the original point. We need to move away from the original point to arrive at the derivative. The way we move away from the original point, it brings about the difference in the way we express this approximation. In case of the backward difference, we move backward to the original point. In case of forward difference, we move forward to the original point, and correspondingly we have two different ways of approximating the derivative of a given function. Now these are the things that we have covered in our previous lecture. Now when you consider these two expressions, there is also a similarity associated with it. That is, when you look closely, the first term of this approximation, be it backward difference or be it forward difference, the first term of these approximations, it is the rightmost term, or it is the term where the x value is the highest. So when you consider the backward difference, we are considering 2 points, x minus delta x and x, and the first term in the numerator is associated with the x, because x assumes the greatest value, or it assumes the greater value between these two terms here. Now when you consider the backward or forward difference, we are considering two terms, x and x plus delta x. In these two, x plus delta x is of greater value, so therefore it assumes the first term here. So even though there is a significant difference in backward difference approximation and forward difference approximation, the similarity is the first term in the numerator is always the one that is associated with greater value of the variable. So it is associated with the variable that assumes the greater value. So x and x minus delta x, in this case x assumes the greater value, so that is the first term here. In case of x and x plus delta x assumes the greater value, so therefore we assume it is assumed to be the first term here. So this is a convention that we follow, and so when we follow this convention, we saw that we will be able to arrive at identical answers, identical values or similar values when you consider both backward difference approximation or forward difference approximation. When you take an arbitrary function, you find the derivative of it using backward difference and forward difference. You do not impose any limits, but you just use these approximation schemes and find the derivative of it. We saw that in our previous lecture, it is possible for us to arrive at least qualitatively identical answers. So we take a function, we consider a point in the backward direction, we consider a point in the forward direction, use these approximations, and we saw that it is possible for us to arrive at qualitatively identical answers. So this we saw in our previous lecture, we were able to arrive at the same form of the slope for a given function at a given point. Now when you impose a given condition, it is also possible for us to arrive at a quantitatively precise value for the derivative of a function at a given point, even despite of which approximation we consider. We will be able to arrive at, so both these approximations, it is possible for us to arrive at the same answers using both these approximations here. Now when you consider these different approximations, there is a role played by these approximations in materials research. So often we want to take the derivative of a function while we are trying to describe a given behavior. So in materials research, so one of the examples that we have been considering so far is in the context of thermodynamics. We have been considering the derivative of the free energy, and we refer to it as the chemical potential. There are in several other contexts we want to discuss or describe the derivative of the function. We want to arrive at a derivative of a given function. Now generally there are two different ways we can adapt to arrive at the derivative of a given function. So when you want to find, so you have a function f of x and you want to find the derivative of this function, that is the f of x with respect to the variable that governs it. So there are two different ways that we can adapt to arrive at the derivative of a given function. Now one approach, so there are two different approaches you can adapt to arrive at a derivative for a given function. So this function can be it can arise in the context of thermodynamics, or it can arise in the context of say mechanical behavior or physical metallurgy, irrespective of it. Generally there are two ways we can arrive at a derivative for a function. So it is possible for us to arrive at a derivative for a given function. So one way is the conventional way. So let's call, you can also refer to it as the for our understanding we can refer to it as pen and paper approach. What we essentially do is we consider the function, we try to rearrange the function. So we are given with a function, we develop a function, we try to rearrange the function. So the reason for rearranging the function is it becomes approachable to us. Then what we essentially do is we consider certain theorems or axioms and some formulae that is known to us. So we take a function, we look into it, we consider it, we develop the function, we rearrange it, make it approachable, then we introduce different theorems, axioms and formulas, and then we ultimately solve for the derivative. We ultimately derive the derivative of this function. We solve by hand, we consider each and every step and we will solve it by hand, and we ultimately arrive at the derivative of this function. So this is one way of going about. Now in your school days and in the early semesters, you would have adopted this approach. Functions would have been given to you and you would have solved it by hand. So you would have considered all these different steps that are involved. You would have your derivation would have involved several formulas, several theorems, and ultimately you will end up with an expression that is the derivative of the desired function. So this is a conventional way, this is pen and paper way, or you can also call it as an analytical way of approaching the given function and arriving at its derivative or deriving its derivative. Now there is also another way of considering or estimating the derivative of the function. It is called as the numerical approach. So what numerical approach essentially involves is we consider a set of iterative operations. We break down the entire problem into small pieces and we consider a set of iterative steps. We consider a set of iterative steps, and then ultimately by combining all these iterative steps, we would ultimately calculate the derivative of the function. So means an iterative step is involved. Generally, in order to do this a form of a calculation regularly, iteratively, what we use is we generally use a computing machine, which we refer to as computers, of course. And since these computing machines are involved, so therefore these approaches are called as computational approaches. So there are two ways. So essentially in the numerical approach, what essentially we will not be doing is we will not be involving numerous axioms, numerous formulas, too much things we will not be involving. We will break down the entire problem into small pieces. We will consider an iterative operation, and ultimately through this iterative operation we will try to arrive at the derivative of the function. So there are advantages to both conventional and numerical techniques. Numerical techniques, they involve certain approximations, and we need to fine tune certain parameters in order to arrive at we needed to have a refined exact answer. In case of the conventional approach, since we are not making any approximation, we are involving axioms, theorems and formula that gives us the exact answers. So the accuracy of the convention is often, the conventional technique or the analytical technique is often more precise than that of the numerical one. So numerical ones, they begin with some approximation, they break down the entire problem into smaller steps. So there are certain approximations involved, there are certain combinations involved. So due to that, there might be a loss of accuracy, a loss in accuracy, but it can be rather perfected. You need to take additional steps to perfect it. But in analytical approach, So we are following the conventional treatment, we are using or we are adapting the techniques that has already been established. So the accuracy is generally more is greater when compared to the numerical approaches. Of course, like I said, the numerical approaches can also be refined and it can also be enhanced. But there are functions, particularly the functions that are related to the physical systems, that cannot be approached directly by the analytical treatment. So such treatment, they do not have a well-defined solutions. So in that case, we need to adapt the numerical approximations. So let me repeat, particularly there are functions in the physical world which cannot be approached by analytical treatment. So there are no definite or well-defined analytical solutions or conventional solution. So in those cases, we need to adapt the numerical treatment. So therefore, this numerical treatment also plays a key role in materials research. So even though there are two ways of handling or arriving at a derivative of function, both have their advantages and disadvantages. When you consider a physical system, the numerical treatment of arriving at a derivative is rather preferred because we don't know if the solution for a given function, particularly the derivative of a given function, is it well defined for a given condition. We don't know. So therefore, we adopt numerical approach than the conventional approach. Of course, when you consider the accuracy, the conventional or the analytical treatment is more accurate, but since often we don't know the nature of the function, we adopt the numerical approach. Secondly, often the derivative that we consider is often a progressive one. So the derivative needs to be calculated numerous times. So in those cases, the numerical treatment, it has an advantage over the conventional one. So when you need to make numerous calculations and when you have to have the solution that is periodically being updated, so in those cases, the numerical approach will be more beneficial to us than the conventional one. So conventional, it has its benefits in the advantage, or it has its benefit in the accuracy, whereas the numerical treatment can be adapted to treat any given function. Without knowing what would be the nature of the derivative, we will be able to treat any given function. Secondly, often it is required of us to calculate a given derivative numerous times, and we need to update this derivative. So in those cases, the numerical treatment is beneficial to us. So therefore, in the framework of the material research, numerical treatment is largely adopted, and we will be spending considerable amount of time in talking about the numerical approximations and how it is possible for us to arrive at a different derivative using this numerical treatment. So owing to the role the numerical approximation plays, or the numerical treatment plays in the materials research, we will be investing considerable amount of time, or relatively greater amount of time, in talking about the different numerical aspects or the different numerical treatments that can be adopted to arrive at or to formulate the derivative of a function. But relatively, we will be spending a less amount of time, we will be investing less amount of time in the conventional or the analytical treatment. However, we will be considering the critical theorems that is required, that we need to understand when we want to adapt this conventional approach to address or to find the derivative of a given function. So owing to the role of the numerical function, we will be considering we will be placing it in a prominent place, relatively in a prominent position, and we will be investing a greater degree of time on understanding the numerical approach for this derivative of to identify or to calculate or estimate the derivative of the function. However, the analytical treatment also plays a role. So therefore, even though the time that we spend on the analytical treatment will be relatively less, we will try to include, or we will try to consider some critical theorems, formulas and axioms that will help us to handle a given function using this pen and paper or the conventional approach. So we will not totally get rid of this conventional treatment. We will try to involve some theorems and some formulas, so that even when we have a function and that appears to be approachable through this pen and paper technique, we would be able to do that. So for that reason alone, we will be spending relatively less amount of time in the conventional treatment of a given function. So the reason why we are spending more time, or we intend to spend more time on the numerical approximation, is primarily because in material research, when compared to the conventional treatment, the numerical treatment plays a prominent role. So for that reason, more time will be spent. However, we will not be totally ignoring the conventional treatment. So now, having distinguished our different approaches of proceeding to find a derivative of the function. So we have considered two different approaches that one can adapt to find the derivative of the function. Now let us see what is the use of this approximation that we have so far been considering. So we have spent some time to discuss or to have the expression that is based entirely on the definition of derivative. Let us see if there is any use for this approximation, particularly in the framework of conventional treatment. So what I am talking about is we have spent some time to arrive at this expression here. So we have been spending some time to discuss about this expression here. So this expression is entirely based on the definition of the derivative. So in order to arrive at this expression, or in order to, we have been spending some amount of time on this expression alone. Now what we want to do is we want to see if this expression that we have been considering thus far, is it as, or does it have any significance? Does it really play any role, particularly in the conventional treatment? Can this expression that is entirely based on the definition of the derivative, this approximation, does it play any role in the conventional treatment of our derivative? So of course we will come back to the numerical treatment. For now, let us see if this approximation, does it have any significance in the conventional treatment of the derivative. In order to do so, let us consider a function that we are familiar with. So let us consider a function such as this, a univariate function, that is f of x is equal to x power n. So n is a constant and x is the variable, the single variable that governs the function. So what we have is a univariate function. Now, in our classes earlier, it would have by now you would know by heart that the derivative of this type of a function is n x power n minus 1. So this is something that now you know by heart, because you would have used this formula numerous times, and you would have learned it separately, and you would have used to solve a certain function, you would have used to solve a certain derivative of certain specific functions. So by now this expression of this, rather the answer for, rather derivative of this sort of function, you would know by heart. Now let us see how we will be able to treat this function if we assume this approximation that we have considered thus far. We will see what is the answer this approximation would give us. So we have these two approximations. What is the outcome this approximation would give us when we try to find the derivative of this function using this approximation? So we have a function, we know what is the derivative of the function is, it is known to us. Now what we will try to do is we will try to find the derivative of the function using these approximations here, and then we will compare the outcome and see how it is beneficial to us, and let us see if it is beneficial at all. Okay, so that is what we will be doing in this subsequent section. So we will adapt the forward difference approximation. So according to the forward difference approximation, the derivative of this function is f of x plus delta x, again it is an approximation, minus f of x divided by delta x. So now let us begin with the expression for x plus delta x. So we have a definite function that is here, we want to find the derivative of the function. Now what we are doing is we are considering a point that is beside x, that is x plus delta x. When we do that, what we need to find is x plus delta x the whole power n. Now it is possible for us to expand this term here using something called as binomial expansion. So using this binomial expansion, it is possible for us to expand this term. I believe it was from Pascal that we arrived at this expansion, or it is Pascal who gave us this expansion. Of course, there is this wonderful Pascal's triangle that is closely related to it. So therefore, it could be Pascal who gave us this expansion. So it is possible for us to expand this term here, that is x plus delta x the whole power n, as something like this. That is x power n plus 1 by, or n by 1 factorial x power n minus 1 delta x plus n minus 1 2 factorial x power n minus 2 delta x square So let us consider, I believe we are able to see a trend here, but to establish this trend, let me consider also a third term, that is n minus 1, n minus 2 divided by 3 factorial x power n minus 3 delta x cube, so on and so forth, and ultimately we will end up with delta x power n. So what we have done is, we are considering the first term of this approximation, the forward difference approximation. We are considering the first term of it. We have treated the first term with respect to the function that we are interested in, and we have expanded it using binomial expansion. That is all we have done. Considering the first term, expanded it, or considering the first term in the context of the function that we are interested in, and then we have expanded it. So we have this expansion, and if you compare these three terms here, you will be able to see a trend how this whole expansion progresses. So there is a way this whole expansion progresses, and if you compare each of these terms, so you will see how the delta x increases in power, and how we have n power minus 1, minus 2, minus 3 and so forth, and how these pre-factor, that is n minus 1, n minus 1 and n minus 2, how these progresses. So there is a trend associated with it. So this is nothing but the expansion of the first term. So the second term of the numerator is f of x, that is nothing but x power n. So the second term of the numerator is just the function, that is x power n. Now what we want to do for the numerator is, we want to consider the difference between these two terms. So f of x plus delta x and f of x minus x. So we need to consider the difference between these two terms. So when you combine this, so f of x plus delta x minus f of x would be nothing but, we will try to rewrite this entire term by considering fewer terms. So x plus x power n, n by 1 factorial x. So I'm just rewriting it with fewer number of terms, n minus 1 to factorial delta x squared dot dot dot. So we will go to the last term, that is delta x power n, and now this is minus of f of x, that is x power n. So x power n. Now what ultimately then happens is, it is possible for us to cancel these two, and then what we are end up with is, so we will what we are end up with is the difference between f of x plus delta x and f of x is n x power minus 1 delta x. So what we have done is, we have treated this 1 factorial as 1, yeah, and then we have the next term n minus 1 by 2 n minus 2 delta x square, so on and so forth, and ultimately delta x power n. Alright, so all that we have now is an expression, a set of terms that describe the numerator for our approximation. So we were able to arrive at a set of an expression that describes the numerator of our approximation. Now when you want to approximate the entire derivative, that is d of f of x with respect to d of x, all we need to do to the numerator is divide it by delta x. So all we need to do is divide it by delta x. So this would be 1 by delta x of x. So the second term by 2 x, or rather x power n minus 2 plus delta x square, so on and so forth, and ultimately delta x the whole power n. So all that we have done is, we have rewritten the numerator along with the denominator delta x. Now if you take this delta x inside, multiply each and every term associated with the numerator with delta x, what we then would end up having is this derivative of the function from the approximation. So the derivative of this function f of x, which is x power n, the derivative of this function from the approximation alone, what you would get is, you are taking the delta x inside, so therefore the first time the delta x gets cancelled out. So n x power n minus 1 is the first term. The second term would be, so there should not be any plus here, so the second term would be n minus 1 by 2 x power n minus 2, and then there will be a delta x. It will no longer be delta x squared because we have brought it in and the 2 gets removed, so on and so forth, and the last term would be delta x power n minus 1. So this description or this expression to calculate the derivative of the function we got from the approximation, from the forward difference approximation. Now we have this expression here, purely from the forward difference approximation we have this expression here. Now we already know what is the derivative of this function is, that is, we already know the derivative of our function is nothing but nx power n minus 1. So this is known to us. Since it is known to us, it is possible for us to calculate this exact formula to that of the approximation that we have derived. So we have derived an approximation, and now we are comparing the approximation to the exact formula that we already know. So if you compare these two, we can realize that the exact answer is already found in the first term alone. If you consider the first term alone of this approximation, we have already established the right answer. We have already established the exact answer. So what it then means is all the rest of the terms here, they contribute to the error. So let me repeat. What we have done is we have taken a function, we have used forward difference approximation to arrive at an expression that is here. Now this forward difference approximation should give us the answer for the derivative of the specific function that we are interested in. Now since the answer is already known to us, we are comparing the approximation to the answer that is known to us. So when you are comparing the approximation and the answer that is known to us, you observe that the first term of the approximation in itself gives you the exact answer. So then what it means, so you cannot further refine the exact answer, right? So you already know what the exact answer is. So whatever additional terms there are then in the approximation, they essentially contribute to the errors. So therefore we refer to them, or we categorize them as the error terms. So error terms or error functions. Now when we want to arrive at, so when we want to change this approximation to the exact derivative, what we need to do is we need to get rid of this error terms. So if we are able to get rid of this error terms, then ultimately the approximation answer and the actual answer will be the same. So we have an approximation answer, and since we already know the actual answer, we have compared it and we were able to identify a set of terms as the error terms. And now if we are able to get rid of this error terms, then ultimately your approximation, the answer for the approximation that you get, will be equal to that of the actual answer. Now how can we get rid of this approximation, or how can we get rid of this error terms? If you look closely, all these error terms are associated with a key parameter or key term that you observe in all these error terms. A key factor that you observe in all these error terms is, so one of the similar factor that you observe in all these error terms is delta x. So to see it here, you see it in the subsequent terms, and also you will see it in the end term. So all the combination of these error terms are nothing but a function of delta x. So we can write the approximation that we have got as, this is an approximation that we have thus arrived. We are able to write, or we can categorize these terms as error terms, and we can write it as a function of e that is dependent on delta x. Now when I introduce a condition, that is limit delta x tends to 0, when I introduce this condition, then the role or the influence of each of these terms in changing the first term significantly decreases. So we have this term, that is the actual answer that we desire in. This we know because we already know the answer. So there is an actual answer that we desire in. But in order to change the answers, there are several associated terms in the approximation that attempts to change the precise answers, and you identify that there is a term that is associated with each of these individual terms that attempt to change the precise answer. So in all these associated terms, there is a factor that governs all of these associated terms that tries to change the actual answers, that try to compromise the actual answer, the exact answer. So we are introducing a condition based on this factor that tries to compromise the actual answer, that is limit delta x tends to 0. And when we do that, the influence of the error on the actual answer significantly decreases, and when it is close to 0, when the delta x is close to 0, all these terms vanishes off. When it is exactly 0, all these terms vanishes off, and when it is close to 0, the influence of these terms become minimal on the actual answer. So ultimately, when we impose such a condition, that is limit delta x tends to 0, then the derivative is nothing but it becomes equal to that of n. So this expression, so the derivative becomes equal to this expression here. Now this we derived starting from the first principle description of what a derivative is. From our first principle understanding of what a derivative is, we were able to arrive at this expression here, and as you can see, this expression is identical to, or this expression is the formula that we use to calculate the derivative of a function that is known to us, that is f of x power n. In order to calculate this function here, in order to calculate the derivative of this function, we use this formula, and the same formula can be derived by considering or starting from the first principle description of what a derivative of a function is. So this approximation, they also play a key role. If you are familiar with, if you are comfortable with handling this approximation, this can also be used. So what is the whole example, this treatment of the function signifies is, if you are comfortable with this first principle estimation, this first principle approximation of what a derivative is, then using that, we will be able to arrive at any given formula that we need for solving a given function. So if you are comfortable with using this first principle calculation, if we are comfortable with handling this first principle expression, then starting from that, even in the conventional treatment, we will be able to arrive at a derivation of a given function. So these first principles approximation, they play a key role not only in numerical treatment, but it can also play a key role. It can also be helpful when you are doing a pen and paper calculation, when you are adapting an analytical treatment for solving a solution. So all that we have done is, we have started off with this approximation, and we have tried to use, or we have expanded this approximation, or we have considered, we have manipulated this generalized approximation to our given function. And after manipulating it, we were able to introduce, we were able to distinguish the answer from that of the error terms. And once we were able to distinguish the answer from that of the error terms, then we were able to introduce a condition, a limit, that allowed us to get an answer that is close to the actual one. So the approximation, it came up with a different set of terms. We were able to identify the error terms, and in those error terms, we were able to identify the common factor, and by imposing a limit based on the common factor, we were able to arrive at an outcome that is close to the actual outcome, that is close to the well-defined formula. So therefore, this first principle calculation, it will be of huge significance if you are comfortable with it, if it will be of huge significance while handling any given function in any given framework. Now, before winding this lecture up, I would like to introduce another notation. So as you can see, these error terms, these error function, of course they are based on, they are dependent on delta x, but the order of the delta x, the power of the delta x increases progressively. So here the power of the delta x is 1, in the next term it will be 2, 3, and so on and so forth. So the order of the principal variable that dictates this function, it increases progressively. So therefore, one common way of writing such a combination of terms. So you have combination of terms, you have a progressive terms, and the power, the order assumed by the variable, it progressively increases. So one way of expressing such combination of terms would be something of that sort. So what it means is that all these terms are increases, they vary in the order of delta x. So all these subsequent terms. So I can replace this, all the error terms, with this expression here, with this function here. So what I mean by that is, this set of terms here can be expressed as, that is d of f of x. So we have the set of error functions that are associated with it. So this can be expressed as something like this. So what it means is that there are subsequent terms associated with this first term here, and all these subsequent terms involved or it is associated with, or the principal variable here in that case is delta x, and the order of the delta x progressively increases. So that is what this particular notation it indicates. So this particular notation, what it indicates is all the terms, the subsequent terms, they are dependent on delta x, and order of the delta x in each and every term, it keeps on progressively increasing. So therefore it is possible for us to replace the function e delta x with this fancy o delta x. So that means the order of the delta x, the variable that governs the error function, increases as you go forward. And now when you impose this limit, delta x tends to 0, the significance of this term here vanishes off. The significance of this term here vanishes off, ultimately leading us to an expression that is close to our well-known or the known expression, the known answer to our function, the derivative of our function. So with this, we have been considering too much, or we have been focusing too much on the expression that results from the description of the derivative. And with this, we have seen what is its role, or how can we employ that understanding of the derivative while we are doing some conventional derivation. So we saw that it can be adapted in this manner, and ultimately depending on how we are able to realize the error function and how we are able to handle it, we will be able to arrive at the derivative of a given function that is as precise as the one that is predefined, the one that is well established. Now with this, we will wind this lecture up, and in the subsequent lecture, we will largely focus on the other mode of solving the derivative. That is, we will largely focus on the numerical treatment. And of course, like mentioned earlier, we will also try to touch upon certain axioms that will be helpful to us. So in the next lecture, we will try to move on to the subsequent aspects or next aspects of involving this derivative, particularly from a numerical perspective. Goodbye.